Good evening. Gavin Clark here from the National Museum of Computing. Tonight we are celebrating an important anniversary in the history of computing. That is the anniversary of the founding of Cray Research Incorporated some 50 years ago on this very day. Cray, as I'm sure many of you will know, and if you don't, I'm going to recap it anyway, was responsible for producing some of the fastest computers in the world at that time. It's of course remembered for the Cray 1, but ultimately it went on to produce, in its various guises, its corporate history went on to produce a number of incredibly diverse computers and product lines all around that high performance threshold. It had some of the world's most serious users at the time, engaged in some very interesting activities in science, industry, in research, and this, of course, was a time when, at a time long before the high performance computers that we have, or servers that we have today, which are founded on commodity systems, Intel servers, running the Linux operating systems. That was a time when systems had to be specially built and they were highly proprietary, and they had a price tag to match and a power draw to match that too. We're here with Clive England, who will take us through the history of Cray and the technology and some of those systems. Clive worked at Cray Research during the 1990s. He was, I understand, a software engineer, and he was involved in the installation, the tuning and troubleshooting on some of these very expensive and very fast systems. Clive is currently researching the history of Cray branded supercomputers too. Clive is going to be talking to us for about 45 minutes. I encourage you to obviously have some great questions for us. Keep them to the end though, just so we can keep on track and on time. If you haven't already, please mute yourself, just so we don't get any background noise and chinking of plates and cutlery, because it is that time of the evening, if you're in the UK anyway. And I think we're all set. So yes, 45 minutes. Clive, over to you.
Welcome everybody, and thank you for that swift introduction there, Gavin. The presentation does have quite a lot of detail. It's probably best viewed on a larger screen if you have one. If you want to put questions in the chat box as we go along, we can certainly look to address those at the end, and I know there are some experts online who can probably pitch in along the way. The only other thing is, please have a beverage of your choice available at the end, as we will be doing a celebratory toast. Right then. So let's get started. To explore, discover and celebrate, we're going to very quickly look through the origin, evolution and revolution. We're going to see who was buying and what for, look at the customers and some of their applications. We're going to explore the crunch time in the mid-90s, where a lot of tech companies, and certainly Cray, had a bit of trouble sustaining their business model, and then the post-year 2000 and the current legacy that we have. So all in all, we're going to try and hit 50 years of Cray Research in 50 minutes. Inevitably, we're not going to cover everything. And then at the end, we'll have our Q&A and our wrap party. So first off, let's roll the credits. The material here is pretty much all in the public domain in various places. In crayhistory.net is the current project where we're gathering a lot of material, but other sources are available. Acknowledgements and thanks to the museum at Bletchley, our host for tonight, and also Computer Museum America and Gene for the excellent images and graphics, and of course all the contributors and reviewers. So with no further delay, let's get right into it. Let's have a look at the genealogy chart of Cray supercomputers all the way up to the year 2000. If we look along the swim lanes, we kind of see mostly evolutionary development, when one machine is improved, refined, and developed into the next one, and then the jumps to different lanes, notably here and down through to here, is where there were revolutionary changes of technology, all aimed at delivering high performance, but the price points varied. So let's get started. Seymour, we're going to have a look at the Cray 1, the origin of the Cray 1, and in detail at one of them, serial number 34, that currently lives at the National Museum of Computing. We're going to look at a little bit at the origin story, the evolution. We're going to glance down at the ELs and review the revolutionary change that high performance computing took to get onto the massively parallel line up here with the T3Ds and the T3Es. Okay, so the origin story. Seymour Cray, noted computer designer, had other successful systems at CDC, which that he had successfully designed and delivered. Between 1968 and 72, he was working on the CDC 68000, which is this machine here, a 4-processor machine, but it only made it as far as sort of partly working prototype. And by which time Seymour had kind of fallen out a little bit with CDC. He didn't like the working environment. He thought the machine needed a redesign. CDC weren't able to do that. So he left and went over to Chippewa Falls with his group of people to found Cray Research. So the 68000 was the direct predecessor, but the actual machine itself was scrapped some time ago. It was only a prototype, but a lot of the parts worked. Ambitiously, it was a 4 CPU system, whereas the Cray 1 over here on the right, shown in 12 column mode, was a single processor machine initially. So the Cray 1 was not his first trip to the computer design rodeo. He had backstory, he had history, and he had had success in designing high performance computers before. So Seymour designed and built the Cray 1, serial number 1, and it appeared in its innovative horseshoe sort of shape with stacks of boards on the outside in each of the columns, and on the inside a wiring mat that joined up the rear edge connectors of those boards. So serial number 1 was a fully working machine. There was a competition, a little bit of a competition between Lanel and NCAR as to who would get it first, and it was settled by Lawrence Livermore Labs getting it for 6 months, then NCAR, and then it traveled the world, going to ECMWF in Reading, AWE in Berkshire, Desbury Lab, some other government customers, before it finally retired to the Chippewa Falls Museum in about '86. It had a brief outing down to one of the supercomputing shows, but largely it's now retired. During that first trial at Lanel, it was discovered that there was a bit of a problem with the machine in that it had 152 single-bit errors discovered by the parity in the memory, and that caused that number of interrupts, which was not really acceptable. Serial number 2 was therefore scrapped, and serial number 3 was built with a different memory arrangement that would handle an auto-correct single-bit errors and detect double-bit errors. This is SecDed. So the secret source, all founders and inventors have secret source in the machine. And for the Cray 1, it was its ability to do fast continuous action. And I like from taking data from memory, pushing it through the registers, manipulating the data, doing all the calculations, and back out to memory at pretty much full speed. And when people ask me, how do you describe vector processing? I like to say, when it's working well, it looks like a slinky going down a staircase, completely smooth, continuous. There are slight changes in action, but it's a full, continuous, smooth action. And when you can get your supercomputer to do that, it will be most productive. So looking again at the origin story, we see Seymour up here on the right with the stacks of boards in each of the columns. And we're not going to crawl over this, needless except to say there were 3 basic chip types in the Cray 1, NAND gates, memory chips and register chips. And all the rest was put together with the wires and the boards, which we'll have a look at in a little bit more detail. And the key bit here is the memory. Notice how there are 8 or 16 banks of memory rather than just one homogeneous memory. And because the memory had a 4 clock cycle period time, you could read from successive banks of memory 1 word per clock cycle and fill up your vector register at pretty much full speed. So it's all about the memory interconnect, the way that the memory would integrate really well and flow the data through the machine. But how do these great specifications translate into a real working machine? So it's time to get your blue coat on, put your static wrist strap on, because we're going to do a little bit of a deep dive into the Cray 1, serial number 34, that lives at the museum. So the first thing to notice about our Cray 1 is that it has 2 sets of 4 columns. We've got individual columns here, and we've got what looks like a group of 4 columns here. That's quite significant, as we'll see in a moment. Each of those columns had about 171 boards, and on the rear edge, 72 pin connectors that would go into sockets at the back of the stack, and these little dangly wires at the front provided plus and minus 5 volts power. The circuit boards with integrated circuits were mounted on copper plates where the heat would be sucked out to the edge, and those aluminium columns had circulating coolant to take the heat away. At the bottom here, we can see these seats revealed. That's where the power and the cooling was fed into the machine, and each segment you could replace one of these individually if there was a problem. So before we go on to that, but what I want to, the first thing I need to get you to look differently at the Cray 1. The Cray 1 wasn't just, in this case, 8 towers or quite often 12 towers of boards. They were actually, each of these towers was split in 2. Okay, and you can see here the bus bar is split at the front here, and on the back there's a slightly different tag about halfway down, showing that you're halfway down the machine. So in fact, this 8-column Cray was really 16 columns, as each column was stacked in 2. So let's have a look, because we need to see in detail about how this machine was put together. Okay, so let's have a look under the yellow star and see what's going on there. So we can just about see that we're 3 columns in from the right hand side, and we're about a quarter of the way down the stack of boards. So let's see what's going on in there. So if we look at our module map here, we can see we've got the 8 columns of the machine, with the 4 on the left being memory locations, like I said, split in 2 here. So there's in fact 8 banks of memory. And in this set of 4 columns, we've got all the business parts, all the pieces that do the separate, hold the separate functional parts of the machine. And I've picked out a couple in color here. We have the red logical units the red vector units that do the different operations, and in green here some floating point units that do floating point, add, multiply and reciprocal. And under our 1, 2, 3 columns in, about a quarter of the way down, we've got scalar addition. Okay, this is where numbers were added up, where it did the 1 + 1 = 2, typically between scalar registers, which were located physically quite close to the scalar addition unit. So we can see that this part of the machine is scalar addition, and other parts of the machine were groups of boards that combine to make a particular function. Okay, so this is all very well, but it doesn't show us how a service engineer would locate a working or non-working part of the machine. And that's what we typically may need to do. Everybody's happy when it's all working. Getting a machine fixed quickly when it's not working is the key to success. So let's have a closer look. We're looking at the scalar addition. And here we have the logical plans that engineers had showing the scalar add boards and how they operated together and were connected together. We can see that 4 boards of type GE were located to do the 4 16-bit parts of the addition, because every word was 64 bits long, so you needed 4 lots of 16 bits to do the addition, and that scalar add split that sum down into the 3 parts. We can also see F44 to F47 being the sort of the coordinates of where our scalar addition boards are, and then these individual wires here would be the blue and white wires in the wiring mat at the back. So we can see we've got our 4 scalar add, and then board type GF at the top of that scalar addition area would do the final addition. Scalar add 1 + 1, fairly simple. There were, of course, vector based addition and also addressed based addition. So that if you can program your machine to do the different operations in parallel, obviously you get a lot more performance out of the machine. And at the bottom here we have a similar map for floating point add, which is considerably more complicated than scalar add. So having seen how the inside of a Cray 1 can be understood, let's take a step back and see what else is needed for the care and feeding of a Cray 1. Power, and lots of it. All of it converted from +5 to -5 volts DC by the motor generator set. And that really is a big motor and a big generator with a little bit of a flywheel in the middle, and that MG set would feed the appropriate type of power into the machine. And about 115 kilowatts, a kilowatt's about a 1 bar electric fire. So that's a lot of power through the control panels via the seats at the bottom into the stacks of the machine. If you're putting that amount of power in, you've got to take it out with the chilled water supply, which fed into a compressor that compressed Freon, and that was the coolant that went in these aluminium columns where the heat was drained out and pushed out to the building chilled water supply. The maintenance workstation was used for starting, stopping and testing. That was typically a small Data General Eclipse machine where the engineers would do special operations on the machine, start and stop it. To get data in and out, you needed a front-end machine, typically a larger IBM MVS machine or a VAX or CDC type machine, and disk drives, tape drives. Again, you needed disk controllers for those. So all in all, you needed quite a collection of machinery. And not forgetting the people as well as operators. You typically had a site engineer and a software analyst, and they would work in the site office. They probably arguing over whose turn it was to buy the milk for the tea, because these are great machines that never broke or ever needed complex troubleshooting investigations. So I'm sure those site engineers and analysts had plenty of time for tea. So we have here some original install photos for serial number 34 when it went in the door at RAE, and we love install photos. It's delivering the dream. It's the start of something big. It was the financial checkbox for new system types, which often were delivered to a more friendly customer who would say that the machine had arrived once it had arrived. But the customer acceptance tests were that final sign off for money. So in this picture, we can see the control terminals, which were traditional single stream terminals. No windowing was involved, and serial number 34 on its specific roll along dolly. And all the machines would have these dollies that were used to move the machine safely from the backs of trucks onto the machine floors. And also in the background here is the legendary Lynn James, a notable engineer in the UK who was incredible, really great engineer. Photos from Charlie Clark, thanks Charlie, whose service story is over on the website. So there we are. After all the purchase and install work, the planning, the preparation, the delivery, there comes that moment when for the first time the system's handed over to the customer. They got to sit down, get ready to start work with the most powerful supercomputer in the world. What problems are going to be solved? What engineering and science is going to be achieved? You have to savor that moment, sitting down at the machine for the first time and getting it going. That is a special time, getting those machines up and running and delivered for a customer. So we see now some Cray ones out in the wild. The row of pictures across the top is at Daresbury Lab, and that's serial number 1. The middle picture showing the IBM 370 that was used as a front end to the Cray 1 to feed the jobs and data into the machine. In the middle row, we've got Meteo France's machine that had a complicated ownership structure, and other French organizations also used it. A couple of other Cray ones here. And here is a picture of Seymour at Daresbury when he visited in 79 with serial number 1. You may notice, depending on the angle you're looking at it, the serial number 1 is a little bit shorter than the later Cray ones because that memory SecDed boards took up a little bit of extra space. So the later Cray ones are taller. So looking at Cray ones and how they evolved, because nothing stayed the same. The original Cray ones started out with that 12 stack, the 12 column approach. And serial numbers 1 to about 19 were the original Cray 1As. Serial 20 to 57 became the Cray 1S, which is an example of which serial number 34 we've been looking at. They added an optional iOS cabinet to separate out IO activity from the compute, and could have 8 or 16 memory banks, and if you had on board. The later serial numbers M1 to M9 came the Cray 1M, and that added the ability to have an SSD, which is effectively a very large chunk of memory that you could use as working space in addition to your actual working memory. So that was a feature of Cray systems, that you could have one of these SSDs to have near memory speed file access. But you'd load your data into the SSD and flow it through the machine at memory-based speeds. And of course, down here on the right, we have a self-portrait created by one of the early digital design customers that used the Cray 1 for photographic work and image creation. So self-portrait. Evolution happened right the way through the design of the machine, and I mentioned that there was evolution and revolutions, and the XMP, the follow-on from the Cray 1, was an evolution. They had double thickness boards, they had slightly different tags on the front, more registers, and the ability to have more than one CPU in the machine. The Cray 2 went a different path. Seymour took it down the total immersion cooling, and we love the Cray 2 because it's filled with liquid, and the coolant actually flows along the surface of these boards, and they're still about the size of a paperback book, but quite a bit thicker than the Cray 1 modules. He went on to do the Cray 3 that again used total immersion cooling. But the first revolutionary step was the introduction of these YMP style modules that used internal cooling. So instead of having power connecting at the front, you connected your coolant into the stacks, and the cooling liquid went inside this module, and you had your power bus connectors at the back, and then along the side you had the signal connectors. And those modules were first introduced as the CPU and the memory modules. And you can see on this YMPD that it's got the same horseshoe style outer edges with the stack of columns that we're familiar from the XMP and the Cray 1. And the iOS function remained using the older technology, while the CPU had advanced using these larger YMP modules. And those modules are as heavy as they look because they're a solid copper container with the processor boards on either side. This is serial number 1001, the first YMP, and that's over in Chippewa Falls. So the YMP level of compute functionality was also available in an air-cooled system. And this is the Cray entry-level machine that was a CMOS version of the YMP, and we're nudging into the 1990s here, about 20 years into Cray history, and we've got about 8 times the compute power for a fraction of the cost, a fraction of the running costs. And being Unix based now, so much easier to work with. There was still batch entry systems you could use, but a lot of this was done direct. A lot of interaction was done directly to the machine using X windows and that sort of thing. Folks that wanted the power of a Cray 1 could get a much better machine for a departmental level budget. This Swansea University EL started as an EL 4 CPU and then was doubled up to an 8 CPU, and that sits just next to serial number 34, but is often ignored by visitors as it looks quite humble. Okay, so let's have a look at customers. Let's have a look at customers, especially UK customers and supercomputing that was done in the UK. And this is a very broad brush stroke we're going to do. There's a lot of machines across that parallel vector history. The main supercomputers in the UK, and when we look at Cray 1 and Cray 2 first customers, we can see it's universities, and we had University of London, Manchester later on, EPCC in Edinburgh, Science and Engineering Research Council. They were all fairly solid users of Cray machines through the years. The big weather sites, UK Met most of the time, Meteo France and ECMWF, the European weather forecasting place, again, had a little bit of an on-off relationship with Cray, but are fairly solid customers. Big Oil used it for a while, Merlin, Shell and CGG for doing seismic exploration. A couple of big military sites, AWE and the RAF, of course, RAE having the serial number 34, but also the engineering companies, the car companies tended to take over as there were less need for the oil companies to have that level of power. Ford, Lotus, Alcan, Ovarp and Hortel Whiting in the UK. Typically Lotus used the ability of an EL to run exactly the same software programs that GM and Ford, who they worked for, used on their bigger systems. Big Science and Big Weather and pretty much were solid customers. Also one or two other places had a continuous stream of Cray machines. But the problem Cray had by the late 80s was what I like to call the Apple trajectory. Everybody likes the anecdotes about Apollonia Cray and Cray being and Max being used by Seymour for the design work on his machines, and the relationship certainly worked both ways. The Cray XMP, which we see here in a rather gorgeous purple, linked to the frame buffer and a mouse to simulate the GUI interface. But the main work for Apple with its Cray was solid engineering and design optimization. We see here some mold flow renderings, making plastic parts. The trick being that when the plastic part came out of the mold hot, it wouldn't fit, and it was only when it had cooled down to room temperature that the plastic would have changed to the right size, shape and coordinates of the drawings, and getting that adjustment right was a lot of time on the computer and specialist applications to get that done. So the Apple trajectory, they replaced their XMP with a YMP2E and followed in the mid-90s with an EL. So they pretty much had a flat compute requirement. Over time, successor systems provided the same amount of compute power, but were much cheaper to buy and to run. And we can see this in the install charts. We can see this Apple trajectory. As the different systems, there's a little of a strata chart here. The Cray ones were pretty much disappeared by the 1990s. The XMPs were fading out, being replaced by the very solid YMP systems, and the C90s and T90s were just being introduced. But we can see what drives the growth in the install base is the orange YMP ELs, the smaller systems here, and the J90s, which were the follow-on machine. So it's time for a revolution in supercomputing. So let's have a look. It's all in a Cray's work. What did they do all day? How did they earn those big bucks? And we can see here some examples from the Cray Channels magazine of particle traces over a F-16 jet, full body crash analysis using finite elements and grids. We've got a bit of computational chemistry, all about solving the equations. The more molecules you add, the harder that gets. And indeed, the state of the art is modeling viruses on current levels of supercomputing. We also had a groundbreaking study of the King's Cross Underground fire that was done on the Cray 2 at Harwell. And here we can see this mesh has changed to a more random mesh. The later systems used that to do their aerodynamic studies. Here we've got a parafoil wing. And of course, we can't forget weather forecasting and later climate research. Huge consumers. As the grid of the world got smaller, the compute demand grows exponentially. And then of course at the weekend, maybe we did a bit of golf club design as well, or a sailing ship hull design for the America's Cup. Maybe at the weekends, maybe not. So here we are. While some supercomputers are doing their day job, improving the structures of cars or understanding engine combustion or airbag deployment, as seen in Hyundai Motors here, there was a special project. Kevin Fox at Cray Bracknell and Swansea University with Mike Ayres were doing the aerodynamic studies for Thrust SSC, the supersonic car and land speed record challenger. Cray was a donating sponsor for Thrust SSC, and they used a Cray C94M, the large memory version of the C90, to do the ISO predictions of pressure surfaces. And here we can see effectively effectively displaying the sonic boom. And this photo amazingly shows that the modeling matched reality, and that's where simulation and when the simulation and physics are correct, that's where you can say that you've spent your money wisely doing the design. This white front here reflects this sonic boom shock profile. Okay, so we're rolling into the mid-90s. It's crunch time. The big supers are not keeping up. There's demand for air-cooled departmental ELs and J90s, but that's not where the money is. The key issues of the big T90s and C90s were simultaneously not having enough CPUs in the machine and also having too many CPUs in the machine. If you've got too many CPUs, the memory interface, the iOS can't cope. If you haven't got enough CPUs, then you can't break down those weather models into their, you can't get enough parallelism into the task. So which way to go? We've got clusters, we've got integrated systems. This was the choice. And of course, it's Cray. We're going to go big, complex integrated systems. And that's what they did. After customer consultation and competitor observation, the T3D was born, and we see one here. It was first set up as a special processor that relied on a nearby C90 showing here for all its I/O. Again, we see special processor existing technology used for I/O and support. And on the front here, this little panel, that's actually an Apple PowerBook running the logo behind there. So we've got our T3D hosted by the C90 at Ford, but some of these were shipped with a YMP2E inside the box. And I believe that's similar to the one Manchester had. So the next development cycle brought the standalone T3E. Again, the same CPU arrangements, which we'll have a look at in a moment, but much lower power consumption than a C90 or those class of machines, which was fortunate, and we'll see that in a minute. It also, GigaRing IOSs were added using the same sort of board logic as the T3E. So this gave the infrastructure for future development. The chips within the system could be upgraded, and then later post 2000 different sorts of chips. So let's have let's put our blue coat back on again and have just a quick look at what it means, what you have inside a big T3E. Here we've got about 866 processors, where these larger ones at the front would run the operating system, and each node would have an EV, effectively a CPU, and its memory, which meant that if you got your program right and it talked to the local memory, every single CPU could talk full speed to its own memory at full speed. But also they could talk to the other memory around the rest of the machine using this sort of 3D interconnected torusy network that allowed redundancy because you have bidirectional networking between the nodes. So if you imagine these all on pins, and then the ends of the pins joined up to make a circular route in all 3 dimensions, that gave you your interior network for your T3E. Groups of tens or hundreds of CPUs could be dedicated to different tasks that would be coordinated by all meet up at this barrier, or all keep working till someone shouts eureka, coordination mechanisms built into the hardware. Memory sections were tightly coupled to the CPU, but could transparently fetch and update data on remote nodes. So much changed with the T3E. This was a genuinely massively parallel processor. Different CPU chips, the operating system now had to work across a bunch of processors instead of just in one. The I/O memory, the memory architecture. What could possibly go wrong? Well, it was a struggle to get it to work reliably. The Met Office was upgrading from a very reliable solid C90 from the traditional MPP range to a T3E. Reboots, the new operating system had challenges. It was effectively a serverized version of an operating system where the different single-use functions like file systems, memory, process maps, all were handled by different individual processors, and they would talk to each other through message queues. The new hardware, that was a struggle. There were partial failures in the hardware, random failures, vibration induced, operating system hotspots caused slowdowns and hangs, and most taxing of all was it was okay over the weekend, reboot on Sunday, but it was slow again by Wednesday. The more user work, and that was represented here by these individual processors, all this user work would cause the machine to gradually get slower and slower and slower until there was a next reboot. And you can't keep rebooting the machine that has to run a strict timetable of weather forecasts or long climate models. So why the Scion 5MX up in the corner here? Not to scale, I have to say. Well, that's what I used to gather data from the acceptance tests, the customer acceptance tests on a trial run through a particular long overnight shift. I had a little spreadsheet up on my Scion, and it was like the little technology helping out the big technology. So as it turns out, as Thrust SSC was getting the job done in Nevada, I just happened to be in Minnesota with the T3E project team. There was absolutely no bragging about, well, at least the UK can make a fast car that works. None of that at all. And following on from that work with the T3E team, it kind of all came together. The motor generator set, the one that we mentioned earlier, actually failed on the C90, and it forced all the work onto the T3E, even though it hadn't been formally accepted by the customer yet. And it had to do the full work for the weekend. They reduced the workload to about 85% of capacity, and the T3E worked perfectly all weekend, delivering all the forecasts on time. The only spare MG set, well, that was up in Edinburgh and was going to take a while to get down. Later, just before the Easter weekend in '98, the critical kernel fix for the ongoing slowdown arrived. And of course, that went in just before the Easter weekend with very little user activity. We weren't going to know whether it was working by the following Wednesday or Thursday. So that was a nail-biting Easter. And I note in my diary that the T3E system call slowdown slugs performance after 3 days was solved by that kernel fix. Later on, Swansea University did aerodynamic studies and wheel structure studies using one of these adaptive meshes for the Bloodhound SSC. So using one lot of high performance technology to get another bit of high performance technology, I like that symmetry. So as we head towards the new millennium, the T3E dominated the top 500 charts for supercomputers for about 8 years, which is pretty unprecedented. Newer chips were made available, more flexible I/O options, and the T3E for all its customers, and there were a lot of customers for the T3E, it actually dominated that end of the century, beginning of the next century high performance scene. There were also our big customers, some of our very big customers. They just have a huge appetite for supercomputers. And around 1999, I think, this was a list of what a certain place in the States had. And they had 4 Cray C916s in a group known together as the supercluster, which was 4 machines joined together by shared SSD units. And I guess that was somebody's answer to, I think we're going to need a bigger Cray supercomputer. There's a legacy from those years of supercomputing and engineering achievements: better cars, safer cars, more efficient aircraft and engines, a lot of medical research that came from those molecular studies, less new oil wells were needed, and critically these days, the understanding of climate and climate change, faster CAD to product life cycles, and really an understanding of what's going on in the world can be achieved when you really know the physics and can simulate things. So let's roll on into the post-2000 era. More relationships, it's complicated. And I'm going to say not all of this is history yet, so I'm still researching this area. But we have a similar sort of swim lane chart. Cray bought Ortego Bay and actually did blade servers and superclusters after all. Some even ran a Windows version of the HPE environment, but mostly they were Linux clusters. Some Cray branded supercomputers came from NEC and SGI because of the relationships we had with them, and some Cray branded technology made its way into other systems. The adoption of the open source Linux Lustre cluster system, file system, improved storage flexibility, and the introduction of a whole new class of processor that came with the merger with Terra brought in sort of graph and data analysis tasks and a special type of processor in order to handle those. And this is kind of, how do we analyze the whole of Facebook kind of question, and how do you solve that? And this multi-threaded processor was aimed at that particular target market. The merger with Terra, where Cray became Cray Inc., kind of brought a bit of a reboot. The heritage from the SV1 and T3D made its way into subsequent computers, but really the next revolution was with the Cray XT3, inspired by Red Storm and Jim at the Sandias lab. discussions with Cray brought out or suggested a new direction for supercomputers, and that formed the basis for all these follow-on systems. The subsequent machines are all about the interconnects, the C Monkey, C Star 1, 2, Gemini Cascades. These are how those connections between the compute nodes are handled. And of course, the individual compute nodes went through a lot of AMD Opterons, but also Intel Xeons and Phi's, and ARM Maxwell and NVIDIA GPUs appeared in the machines as well. But the XT3 was that next revolutionary machine that set the basis for the follow-on machines. We're now where Cray is joined up with Hewlett-Packard Enterprises, and they're scaling out to exascale. As we see here, some of these later machines, the XT5, we can see the T3E heritage as it builds from nodes, except we got 2 processors and memory, to blades, to whole racks, and then whole rows of racks. And this is Oak Ridge's Jaguar system. Interesting, Jaguar got updated, all its internals were changed over, and if you hunt around you can see a stop action movie of Jaguar being updated from one type of machine to another. The infrastructure stayed the same, but all the compute nodes. Here we are, another example of a later machine was Hopper at NERSC. It's a nice cover, and a lot of the machines now have this custom designed cover, but personally it's never quite as awe-inspiring as the original Cray 1 shape, seeing rows of systems. These new systems, later systems, they're also, I believe one's going in an EPCC, and I think we have somebody on the call from there. UK Met in the UK, at NCAR, again a long customer of Cray, are going to be launching their new machine soon. Very quickly through the scaling up and scaling out, and better processors, better networking has literally taken us from a few teraflops in the machine right the way up to exaflops, and that all comes down to the ability to join up hundreds and thousands of very, very competent processors in a network that allows them to coordinate. And the structure and topology of those networks has changed over the years in order to make it work. The power and growth of these top systems has continued with Cray at the forefront. So here we are looking back over 50 years of Cray supercomputers. We can see some outstanding machines from the Cray 1, the Cray 2 and the XMP, all the way around through the C90s and the EL. We can see outstanding machines of design and engineering that kept on delivering the highest performance. We didn't even mention, not even once, the CS6400, the child of the floating point systems acquisition that involved into the 64-way Solaris server that was sold to Sun and by Sun as the Enterprise 10,000. And they made a mint at that. It was the right big machine at the right time. But that had some Cray involvement in, and the lads at Beaverton, shout out to them, turned Spark processors into a supercomputer. Okay, we're up to Q&A. So Gavin, how are we doing? Are we on time and on target?
Yes, we're fine. We've got about 10 minutes. That's really good. Thank you, Clive. If you've got a question for Clive, maybe you could just either pop your hand up or unmute yourself and speak forward, or just drop it into chat. So has anyone got a particular question here for Clive? I've got a couple, but you guys, you can go for it first.
Go on. I'll ask one. Yeah, fascinating talk, Claire. Thank you. So I've got a little bit of a soft spot for the EL98 at Bletchley. That spent a few years in my garage on its way from Swansea to Bletchley. As you say, when you walk into the museum, everybody's fascinated by the Cray 1, and the EL98 tends to be a little bit overlooked. What are the chances of getting a Cray 1 operational?
You kind of need to look at the infrastructure required for a start, the amount of power, the amount of cooling. That chemical that they used for the cooling, Freon, I'm not even sure they are allowed to have that anymore. And also, when machines came to the end of life, the choice was you scrap it, or you return it to base, or you put it in a museum by making it still have a good stack or two of boards, but the rest of the boards went off for recycling. So there are some Cray machines that people have ELs going, J90s, and obviously the later machines are all going, but the Cray ones, that would be a big stretch. There are a couple of enthusiasts out there who have Cray 1 emulators built into something about the size of a desk model or a Raspberry Pi. And indeed, there's a project out there to get a Cray 2 emulator going as well. So the logic and the understanding of the machine by replicating its logic is probably what is achievable now, rather than getting an actual physical Cray 1 going.
There's nothing quite like the real hardware operating there.
Absolutely. So it's good to see that there are quite a few ELs still going, and they have the same CPU architecture as the big YMP ELs. So anything you can do with those, the speed ups you see when you make the changes to your program to get better use of vectors are exactly the same on a full-blown YMP as on an EL.
Just to follow up on that point, actually, Clive, we've got a question from Brian, who actually asked how many classic working Crays are still preserved Crays are still working, and of course my mind goes to the Cray 1s, but getting any idea of numbers?
I'm not aware of any Cray 1s. I'm aware of about 4, maybe 5 ELs and J90s that are still operational, typically in a museum enthusiast context. The ELs are moderately expensive to run, but they run on a cooker socket, so they're not so bad. That's a big difference from 115 kilowatts at 4 and 5 plus 4 and minus 5 volts. So about 4 or 5 or so. But I've shown here locations with Crays on display. There are quite a few in tech museums, and also there are, obviously sites that have running Crays now of the current generation.
And I suppose this is something that struck me was you mentioned, I think it was the YMP EL and the J90s were the big sellers during the 90s, or drove growth at least, when we showed that graph of the big wedge of sales. What had customers been using before Crays? And did they introduce net new workloads, or was it just the same stuff on a faster, better spec machine?
It was providing the ability to scale out existing engineering work that was being done on workstation class machines. So there are certain like structure analysis. You can do a wishbone and a couple of ball joints maybe on a workstation, but if you want to do the whole suspension, or you need to scale out to the whole chassis, you needed to have that bigger class of supercomputer.
And we've got a question here from Alan Hancock. Is it true that Cray nearly went broke trying to perfect the Cray 1 interface to the Freon pipes?
I can't speak to that directly. I haven't heard mention of it. It's the Cray story is a 50-year technology startup story. It really is. Dissatisfied pioneer goes off to do his own thing. Has some initial success, makes and then goes his own way while the rest of the company moves on. Nearly went broke a couple of times, especially during the 90s there. Got taken over, refocused, rebooted, and now 50 years later, we still know Cray has become synonymous with high performance computing. But there are very few tech companies that have survived a 50-year story.
Definitely. Well, and those slowdowns you mentioned, the T3E, is there any accounting for that? Did the engineering just go over ambitious? Did Seymour step back in some way, and therefore they took their eye off the ball? Was there any reason for that?
No, that specific problem was a bug within the kernel that was not freeing up the credentials of a process when a new one was forked and made. So as user did user work in a shell, they would create new processes, and every one got just a tiny bit slower than the one before. So when there's a really busy mix of work, gradually the machine would just accumulate fluff and get slower and slower and slower. It was a relatively small fix, but finding it and finding it that it was there to start with, and then what to do about it, was the experts over in Egan. But it was a software fix.
Okay. And we've got another question here. This is from Jamie, who's asked, and I think I can suspect where some of this is, where you might come from in answering this, Clive. What were the specific considerations that led to the original iconic Cray 1 design? You know, that kind of stack on the horseshoe, and what inspired the original horseshoe bench design?
So the bench, as you saw, was where the power supply and cooling just fed into the machine. So they were completely functional parts of the machine. You could, if one broke, you could in effect service it or slide it out and put it back in. As we saw with the module map of the Cray 1, it really was a matter of getting the cooling right to have that density of boards that you could keep them close together. And that wiring mat at the back was made to very specific sizes for specific wires and specific connections. And really it was a not design optimization. You wanted to get that amount of boards into that space. You had to get the heat out. And that's it's no coincidence that a lot of Cray machines came from Wisconsin, and that's a big dairy state. So they knew about cooling and refrigeration and those sorts of things. But it was design optimization in the original machine that kind of. But you could see from the earlier machines that shape was sort of coming around.
And what about this story we hear, whether it's, if you could elaborate a little bit, the kind of design, the C shape was to keep the number of interconnects smaller, the distance between the cabling shorter, so things were faster.
Yeah, that's certainly true. You could see the number of different boards, and each of those boards has a pin connector on the back of it, from which the necessary wires would come and then go to other boards, according to those logic maps that we saw. Those wires had to be very specific lengths. And also repairs, that wiring mat would get about a foot thick at the bottom there. There were some very skilled people who would visit sites to fix those wiring mats when things went wrong, or if one of those pins made a bad connection at the back of the slide in the boards when the board was slid in.
Sorry, and I suppose, what was the response when people saw this thing? I mean, we look at computers back then, we're used to huge rectangular and square-shaped devices. What was this, I suppose the press response, the kind of the critical response? Did people think this is a crazy looking machine? Was there any kind of sense of what people's reaction was to it?
You could see it was something special. You could certainly see it was something special. It walked the talk, and I think that's probably where its praise and its fame came from. You could have made it a grey box, or you could have made it any color box you wanted. It's what it did, it's what it delivered, it's how fast you could get engineering problems solved that gave it its fame and notoriety, but success, gave it its sales success.
Mm-hmm. It'd be great to see if there's any kind of media cuttings from the time to see what the reviewers said to it as well.
Yeah, there certainly is some, and there also I have a photo of an engineer using an infrared camera to have a look down the stack of modules to try and find a hot spot. So yes, I think I've got one of those over on the website somewhere. I see that's in a question.
Okay. Do we have any more questions? Let's keep an eye on time. I think there's some good stuff through. Do we have time for one more question, maybe?
Yeah, just one quick one, if we don't mind doing a little bit of overtime.
Yeah, sure. Anyone got an last question there?
Or shall we? No. Okay, well, let's roll on then. Let's roll on. It's time to hang up the blue jacket. the anti-static smock, grab a Liney's, head over to Lindy's Steakhouse possibly, or even one of the traditional site hangouts that the staff used to go to in different places, because we need to grab your beverage of choice. Hopefully you have one, because we need to say cheers to 50 years of Cray supercomputers. All the people that made it possible, right? Everybody from the salesman, the benchmark, and of course the hardware and software engineers that it kept them going, being either on call or on site 24/7 in many places. So raise your tinnies or your cups of tea, and cheers to 50 years of Cray supercomputers. Cheers, everyone. Fantastic. Unfortunately, Liney's is not imported into the UK. But legend has it that, or tradition had it, that a crate of Liney's was shipped with each new system. I was never quite sure if it was aimed at the customer or the engineers, but I'm sure it got put to good use.
That's some old school enterprise business practices.
Indeed. So here we are in the wrap up. Thank you for your time and engagement. I hope you've enjoyed it. Presentation was recorded. We may use bits of it, more of it, some of it. And of course, museums will always say exit via the gift shop. So be sure to visit and support the National Museum of Computing. If you're over here in the UK, they're at Bletchley. Computer Museum of America, which is just north of Atlanta. Who also have a great display of machines, or your local tech museum. Ping me for details or any follow-ups, howlers, incorrect statements I made. I'm on Clive at crayhistory.net. Go have a look at the website as well, see what else you find interesting. I'm kind of thinking of doing some posters that would look like better versions of this. My skills maybe as an engineer rather than as graphic design, but I'll get some of the right talent to it. But if you're interested, or getting on a mailing list for some posters, then just drop me a line.
That's great.
Okay, well, thanks, Gavin. Back to you.
No, it's all. Thanks very much, Clive. And if you could just please just show your appreciation for Clive, a virtual or a physical hand clap, much appreciated. I see a number of people signing off and thanking in comments, but if you wouldn't mind just one last huzzah for Clive, that'd be fantastic.
Thanks, everybody.
Thank you, everyone. And and thank you very much, and enjoy the rest of your evening. And if you enjoyed that, and I'm hoping you did, check out the museum's events calendar on tnmc.org events, and you'll see a list of forthcoming events for other speakers as well. Thank you very much. It's great to see you all. Enjoy the rest of your evenings.
Cheers, everyone.